Welcome back to part 2. We're continuing our discussion on the gradient and how we can use it to help us solve for maximum increase, minimum increase, and things like that. So let's take a look at the given surface. We have this function here, 3x cubed minus y squared plus 2xy squared. We want to find the following. Well, the first one says, find the complete point when x is 1, y is 0. That's not too bad to do. That's just, whoops, let me go back to black here. First erase that. There we go. If I want to find the value at 1, 0, I'm just going to, of course, just plug those in. This becomes 3 times 1 minus 0 plus 0, and we get 3. So the complete point would be 1, 0, 3. There's our complete point right there. There we go. Next, find the partials of f. That's easy enough to do. Find the partial of f. So that's going to give us, what's that, 9x squared. That becomes 0 over here, plus 2y squared. The partial with respect to y, well, the partial with respect to y, that's just 0. We get negative 2y, and this becomes plus 4xy. Now the next step, it says find the gradient function. So that's our del f of xy. And if we do this, we're going to get, this is just a list of our partials, 9x squared plus 2y squared, and negative 2y plus 4xy. So this is how we're going to write this. Now later on, when you take other more advanced math classes, you may write it this way, as using matrices. But this is way later. That's later on in your math career. Now we're just going to write it in our vector form. All right, the next part says, find the equation of the directional derivative in the direction of our vector cosine theta, sine theta, at the point found in part A. So take a look here. This is already a unit vector. Okay, we're going to assume it's a unit vector there. It will be, because sine squared plus cosine squared is 1. So let's see here. When we're looking, whoops, sorry about this one. So one thing before we begin, just let's talk a little bit quickly about the gradient. Now the gradient in this case only depends on x and y. So the gradient will depend on x and y only. So when we're talking about the point up here, we don't need the z coordinate. So therefore, our point will just basically be the 1, 0 that we're going to use. It depends on the independent variables. So when we start this, to get our directional derivative, our rule from yesterday is we are going to take the del operator, del f, and we're going to dot that with our unit unit direction vector. So we want to find del f of 1, 0. And we're going to dot that with, whoops, what happened there? Don't know. Cosine theta, sine theta. All right, so let's find the value of our del at 1, 0. Whoops. All right, my computer's going crazy here. So what's this going to be? If I plug 1 in here, 1, 0, we're going to get 9. Plug in 1, 0 into the second one, we're going to get 0 plus 0. So I think that's just what, 0 here. And we're going to dot that with our, of course, our cosine theta, sine theta. And that's just going to become 9 cosine of theta. And there's our answer right there. All right. So for part E, we're mathematicians, we love the part T. If the particle is at point A, which remember this is at the point 1, 0, 3, and it's moving to the point 1, 3, 1. This is where we're going to end. What will our directional derivative be in this case? So we already have our del, so we need the following. We need, of course, our vector, our direction vector. So let's go ahead and find our direction vector. We're going to take our endpoint minus our start point. 1, 3. We only want the x values, x and y values. We don't need the z values. 1, 0. And of course, this is going to become 0, negative 3. Now, this is not unit, so we have to get it a unit vector. So u in this case will be, what's that going to become? 0, negative 3, divided by the magnitude of 0, negative 3, which is 3. And we're going to get 0, whoop, that should be positive 3 there. Positive 3, 0, 1. There we go, and there's our unit vector. Okay. Next, to get our directional derivative, def, we're going to take our del operator, remember, our del operator at 1, 0, and we're going to dot that with u. Remember, this is where we're starting, right? We're starting this. And we're going to dot that with u. So we already know this. This is just 9, 0. We got that from part D. 9, 0. Dot that with 0, 1. And we're going to get 0 plus 0, which is 0. Now remember, this at what that's telling us is at the point 1, 0, 3, there is no change in the z coordinate. It's flat, like horizontal. So this is telling me this is the change in the z coordinate right there at that point. All right. So for part F, let's take a look here. In what direction should we move if we want to move in the smallest value possible? Well, what is this talking about? Well, this they want the minimum increase, or the minimum increase for us right here. So, in order to do that, well, that's just our negative del. And there's our answer. So, we want, whoops, sorry. So, if I'm at the point, so remember, we're at the point 1, 0, 3. Right? We're at the point 1, 0, 3. So I want the minimum, I will get negative del of 0 of 1, 0. And remember, we already know that this is going to become negative. And if we take a look up here, del of 1, 0, we already know that that's 9, 0. So it's negative of 9, 0. And there we have it. There's our answer. So that would give us the direction of minimum increase. So I hope, now, I can also find its magnitude, remember? So the second thing, now again, this is not part of this question, but you're going to see this today on your homework. So let's go ahead and answer another part of this. Let's say we want the value of the minimum increase. The value of the minimum increase. So that's just going to be the magnitude of this. The negative of the magnitude of del F. So that's going to become negative the magnitude of 9 squared plus 0 squared, or negative 9 in this case. Right there. All right. So I hope you guys enjoyed this video. Go to part 3. We'll take a look at a few more examples. I'll see you then.